Okay, hi everybody. So I'll try to first solve this, and then after solving it, I'll just sort of discuss it in case there's some concepts that we need to review. So first I'm just going to solve. Find the basis for the tangent space at some point P. Then do the same for the normal space. Okay, so A. Let F from R2 to R3 parameterize the sphere. So let's take part of the sphere and send t to f of t, where really this is an element of R2, so it's t1, t2, some two numbers, and we're going to send it to t1, t2, square root of 1 minus t1 squared minus t2 squared. This actually parameterizes half of the sphere, namely the upper half. Okay. And so, for example, the point 1/2, 1/2 goes to the point 1/2, 1/2, root 2 over 2. I believe. Let's check that. This will be minus 1/4, minus 1/4. So that's minus 1/2. 1 minus 1/2 is 1/2. The square root of 1/2 is root 2 over 2. Okay. Now, the linear map df, the derivative of f at the point t, has its image equal to the tangent space. I mean, maybe I should have said this the opposite way. The tangent space is defined to be the image of this linear map. And so the tangent space has, in this point, it's at the point f of t, and it's the tangent space to the sphere. Okay? At the point f of t. So like that point. Or arbitrarily that point. Okay? So, great. So what is this linear map, the derivative? Well, as a matrix, dft is equal to, okay, so derivative with respect to t1 is there, and the derivative with respect to t2 is there. Those are the two columns. So with t1 I get 1, 0, and here the derivative with respect to t1 will be minus t1, or minus 2t1 over the square root. So this is just how we differentiate square root. So that was the partial derivative of this function with respect to t1, gave this component. Oh, but that's only one column. So the second column is 0, 1, and then partial derivative with respect to t2 is going to be this, t2 over square root. Okay? So df at the point 1/2, 1/2 is, we plug in, 1, 0, and now I have to plug in 1/2 to this. So on the top, I'm going to get a minus 1. On the bottom, I'm going to get a square root of 1/2. But square root of 1/2 is the same as root 2 over 2, and I'm dividing by that, so I'm going to get 2 over root 2, and then a minus 1 hangs out from the numerator. Okay, and over here I have 0, 1, and the same thing. Hopefully I did this right. You can check me. If not, then the correct answer has a different number right here and here. So these two vectors in R3 form a basis for t of f of t at S2 at t equals 1/2, 1/2. Okay, so that's the answer to problem 1. Pause for a moment and just try to make sense of what happened. If not, at the end, I'm going to come back and explain in more detail. Part B, now do the same for the normal space. Okay? So part B, there are now two ways to do this. So the normal space is always determined from the tangent space as the orthogonal complement. So n at f of t of S2 is the orthogonal complement. This is from linear algebra to the tangent space. Okay, and so this is also something you'll learn in multivariable calculus. So the normal space is the orthogonal complement, which means if I have a basis here, all I need to do is get a vector orthogonal to both of these vectors. So sort of my picture is that at some point on the sphere, I have two vectors, and they span a plane, and that plane is sort of tangent to the sphere at this point. Okay, and then what I need for the normal space is some vector that's orthogonal to both. So 90 degrees to TP S2. Okay, so I need that vector, and that will be a basis for the normal space at the point P to S2. Okay, so just a basis is given by the cross product because we're in R3, special to R3. So I don't like that because it only works in R3, so let's find another way. A basis is given by solutions to the linear equations let's see, x1, x2, x3 multiplied by 1, 0, minus 2 over root 2, 0, 1, minus 2 over root 2, equals, so this times this will give actually two equations. Well, it has a row vector, I suppose. In linear algebra, we learned that a 1 by 3 matrix multiplied by a 3 by 2 matrix give a 1 by 2 matrix. And so this is actually two equations, two linear equations. In linear algebra, you'd also call this, the solutions would be the left kernel of dft of that matrix. Okay, or the left null space. This is all linear algebra. Okay, so, I mean, we're taking algebraic geometry. This is nonlinear algebra, but in order to do it well, we first need to know linear algebra. Okay. Great. Now, I will give yet a third way to get the normal space. So what is a third way? So option 1, option 2, option 3. The normal space is also given by the row span of dg at P if g is a function giving S2 as its preimage. So over here, we wrote S2 as the image of a map, F. Over here, we're going to write S2 as the preimage of a map, G. What is this map? Well, let's invent names for R3, and we'll send that to the number, that number, okay? And so what is dg at the point x? Well, I take the partial derivative with respect to x1, and I get 2x1. I take the partial derivative with respect to x2. This is how we take the derivative, partial derivative with respect to x3. And this is a 1 by 3 matrix. And the row span, so row span of this is equal to n x s2. X was the name I invented for a point in R3, but if x is also a solution, I mean, I could have called this p. And so, I mean, we have p, right? P was given to us. P is 1/2 root 2 over 2. So then dg at p is 1/2 root 2 over 2. And so this is a basis for np of S2. And let's check that it solves this equation so that everything makes sense. So what's the dot product of this vector with this vector? 1 plus 0 plus negative 2. Well, that's not right. Oh, no, negative 2. Well, that's not right. Wait, what did I do? 1. Okay, clearly I made some mistake. I'll sit here until I figure it out. Okay, could it be that I plugged in wrong? Okay, let's check that. Do you understand what I'm saying? Like, if this is a basis for the normal space, it has to be orthogonal to both these because these are a basis for the tangent space. So let's try to see what I did wrong. Did I plug in okay? Let's see, 1/2, 1/2, 1/4, 1/4, 1/2 root 2. So that's, if I multiply the top by root 2 and the bottom by root 2, I get root 2 over 2. And then up here I had a minus 2 times 1/2 is 1 over root 2 over 2, which is the same as minus 2 over root 2. Okay, that seems correct. Could it be that this is not even a point on the sphere? Let's check that. Let's check if this is even a point on the sphere. I need to sum their squares and get 1. So 1/4 plus 1/4 plus 2 over 4. No, that worked. That's 1. Okay, so this is a point on the sphere. What did I do wrong? Minus. Did I take the derivative of this correctly and get this? Minus 2t1 over. Oh, I see what I did. Okay, what's the derivative of square root of x? The derivative, okay, I found my mistake, is, well, I should have done this, like 1/2. Now it has to be x to the negative 1/2, but you have to multiply by 1/2. Okay, I think, wait, how did you do the derivative? Yeah, like x to the third, take the derivative, and you multiply by 3, and then you subtract 1 from the exponent. So I have to multiply by 1/2, and then so this whole thing should have had a 1/2 here, should have had a 1/2 here, which means those 2's cancel. There's an extra, so this is a 1. This is a 1. Great. And then this is a 1. This is a 1. And now look, this thing, dot product with this thing, gives, I'll just write it out. This dot product with 1, 0, minus 1 over root 2 is in fact 1 plus 0 plus minus 1, which is 0. So the normal space is orthogonal to the tangent space, and you can check with this one too. Okay, so this is my answer to the normal space and tangent space. And the reason I put this in here is because I don't expect you to remember this, but you did learn this in multivariable calculus, where you should learn the derivative of maps in higher dimensions. Okay, so like the derivative of a map from R2 to R3 is something that's in multivariable calculus. And the other thing is linear algebra. And so rather than just assume you know these perfectly, I did not know these perfectly. And so that's why I'm putting this question in here. This stuff is basic. Basic not meaning easy. Basic meaning we cannot understand more math without first understanding these two subjects. Okay. So please ask me questions about this. I do not expect that this is easy. I do not expect you to have even known this. And so let's take our time. Take our time and learn this. Take our time. Because I guarantee this stuff comes up everywhere. There's no point in learning algebraic geometry until we know the basics of higher dimensions and derivatives, and the basics of linear geometry. Degree 1 polynomials before we do degree 18 polynomials.